Okay, so today I'm going to speak about the Rogers-Ramanujan identities. So the motivation is twofold. First is that since Dr. Matthew told me that there will be a lot of students, so I thought it would be nice to know something about the work of Ramanujan, because everyone is familiar with the story of Ramanujan's life. But as a student, at least when I was a student, I was not very familiar with the work of Ramanujan. I knew bits and pieces, but I did not know any proper sort of like theorem or any theory that Ramanujan did. So I thought it might be nice for the students to see something tangible that Ramanujan worked on. And second motivation was that this topic, Rogers-Ramanujan identities, gives a very nice introduction to different ideas in number theory which appear. So one of the primary ideas that I am going to use in the later part of the talk are about integer partitions. So this talk is roughly divided into two parts. In the first part, I'm going to sort of motivate or sort of show you how Ramanujan might have conjectured these Rogers-Ramanujan identities. And that part will be very elementary. I mean, it just uses the concept of a geometric series, infinite geometric series. And that will be the first part. And then once we are able to conjecture the Rogers-Ramanujan identities, then I'm going to give a short proof of at least one identity of, there are two identities. So I'm going to give a proof of at least one of them, which is due to Ramanujan. And then I'm going to give a combinatorial interpretation to those identities where the concept of integer partitions, they appear. So let me, before I begin, let me just say that since the talk is not very difficult, at least the first part, so if there are any questions in between, please feel free to ask me. I'm happy to clear the doubts as I go along. Whatever I'm going to say today can be found in two sources. The first is a very nice book whose title is actually the title of the talk. The book is called An Invitation to the Rogers-Ramanujan Identities, and it's written by Andrew V. Sills, and it's published by Taylor and Francis. So it's a relatively new book. I think it was released in 2017 probably. So it's a very nice book. And what I'm going to say today is roughly covering chapters 1 and 2. Not everything, but it covers two chapters, 1 and 2. And the second resource is a very nice article by Gaurav Bhatnagar. So he has actually the first bit where I'm going to show you how to conjecture the Rogers-Ramanujan identities I learned from Gaurav. So he has sort of like a series of articles where the title is like, how do you conjecture something? No? So how do you conjecture the Rogers-Ramanujan identities is one of his articles. And it's a very nice introduction to the Rogers-Ramanujan identities. And the third recommended resource is a book by George Andrews, which is called The Theory of Partitions. At least the later part of the talk will depend on some bits about partition theory. And if you want to know more about it, then you can take a look at the book by George Andrews. So these will be sort of like the references for the talk. All right. So just a brief history of, let me just state the identity. So there are two Rogers-Ramanujan identities. The first identity is something like this. So 1 plus q divided by 1 over 1 minus q plus q to the 4 divided by 1 minus q square plus q to the 9 divided by 1 minus q square, 1 minus q cube. Plus and so on, and this is equal to, it's a product, so 1 minus q6, 1 minus q11, 1 minus q16 times 1 minus q4, 1 minus q9, 1 minus q14, and so on. So this is the first Rogers-Ramanujan identities. I mean, if you want to write it in a more succinct form, then this is a sum where the numerator is actually q to the n square, and the denominator is now a product of 1 minus q to the k, where k is going from 1 to n. And then the sum is running from n equal to 0 to infinity. And on the right hand side, again, this is two products. So the first is 1 minus q to the 5m plus 1, and the other one is 1 minus q to the 5m plus 4, where m is going from now 0 to infinity, and this is in the denominator. So this is the first Rogers-Ramanujan identities. Yeah, so this is the first Rogers-Ramanujan identity, and the second Rogers-Ramanujan identity is similar. So instead of n square, I'll have n square plus n. Let me just write it. So n equal to 0 to infinity, q n square plus n divided by product k equal to 1 to n, 1 minus is equal to 1 minus q 5m plus 2, and 1 minus q 5m minus 2. So maybe plus 3, which is the same thing, and then I can start from 0 to infinity. All right, so these are the two Rogers-Ramanujan identities. If you look at them, then we have to, I mean, before we can understand the identities, we have to set a meaning to what it means for a sum and a product to be infinite. So on both sides, you have two quantities. So in the left hand side you have a sum, which is an infinite sum, and on the right hand side you have a product, which is an infinite product. And the amazing thing about this identity is that these two things are equal. So a sum, infinite sum, is equal to an infinite product. So that is the most amazing thing about these identities, and that is why these identities are considered to be really beautiful. So before we can see how one might come up and guess such an identity, let me just give a brief history of these identities. So as I said, these are the two Rogers-Ramanujan identities. I'll call this 1 and I'll call this 2. These identities were first proven by a British mathematician called L.J. Rogers in 1894. But these identities were not really widely known after Rogers' proof. So they became more widely known after Ramanujan wrote them down and sent them to Hardy in 1917, if I'm not wrong. And Ramanujan was not able to prove these identities. But later on, while going through some of the old volumes of the Journal of the London Mathematical Society, he found that Rogers had already proven these two identities as well as several other identities. And then they got together and Ramanujan gave a separate proof of these identities as well as a proof together with Rogers, which they published around 1919. So after that, there was like a lull because people thought that these were sort of like isolated incidents. So identities of this sort were probably not of this type were probably not known. I mean, probably could not be found, and people did not really look carefully at them for some time. But then there was a sort of like an explosion in the 1960s and later on, which is continuing even today. So we'll see some of these later identities, which were proven by people like Dyson, Basil Gordon, Lucy Slater, and so on. So this is sort of like a brief history. Now let me just start with something very basic, which is known to everyone. So that is the infinite geometric series. So why we want to do that is because we want to give a meaning to the infinite sums and products that appears in the identities. So let's start with something which everyone knows, which is this identity. So 1 plus q square, and so on. This is equal to 1 over 1 minus q when mod q is less than equal to 1. Sorry, mod q is less than 1. So this is known to everyone. So just for the sake of like completeness, let me just give a very quick proof. No, so probably everyone knows this, but so first I'm going to prove that the finite series 1 plus q square up to q to the n, this is equal to, so let me take q to the n minus 1, this is equal to 1 minus q to the n divided by 1 minus q. So how does one prove it? So let's call this side Sn. Then what is 1 minus q times Sn? So if you do the sum, if you break the factors, then what you get is that you'll have something like 1 minus q plus q minus q square plus q square minus q cube, and so on up to q to the n minus 1 minus q to the n. And if you see, this is a telescoping sum. So this term is cancelled with this term, and this term is cancelled with this term, and so on until you meet this term. Okay. So what you are left with is just 1 minus q to the n. And this gives you that Sn is equal to 1 minus q to the n divided by 1 minus q. So you already know this. Now, if you just take the limit of, if you take the limit n goes to infinity, then essentially we're taking the limit of 1 over 1 minus q minus limit n goes to infinity of q to the n divided by 1 minus q. Now, as q mod q is less than 1, so as n goes to infinity, this term will vanish actually. So whatever is here will vanish, and you will be left with only just 1 over 1 minus q. So we have proven this result, the infinite geometric series formula. Okay, this is one way to assign sort of like a meaning to an infinite sum. So you have you take the finite truncation of that sum, and then you take the limit as n goes to infinity. Okay, so far so good. Now, what about the product side? Or I mean, before going to the product side, let me just briefly mention some concepts that we are going to use later on. So, right. So there is a similar, actually, I mean, I can actually skip it. So probably you can already guess what is going to happen to the product side. So even in the product side, you take the finite truncation up to some particular number of terms, and then you try to find a closed product for that whole product of a finite number of terms, and then you take just n tends to infinity, and you say that, okay, the infinite product is whatever this limit is. All right, so this is how you can assign, this is one way how you can assign a meaning to an infinite sum and an infinite product of the type that appears in the Rogers-Ramanujan identities. So another approach is via what is called the formal power series, or the formal approach. So, and this is the approach that I prefer in this talk. So this is called the formal approach, or a formal power series approach. So in this case, in this approach, the q that appeared before, we are going to treat it as a formal variable. We don't assign any value to the q. It's an indeterminate, and we don't care about the convergence or the divergence of these sums and products when we are working with the formal approach. Okay, because we are more interested in the properties of the coefficients than the series itself in this formal approach. So so what we work with is an infinite degree polynomial. So we work with an infinite degree polynomial. Something like this, no? So ak q to the k, and k is going from 0 to infinity. So if you expand it, this is just a0 plus a1q plus a2q square, and so on. So the good thing about this approach, when we don't care about convergence, divergence, and so on, and because we are just focusing on the coefficients here, is that we can add, subtract, and multiply, and in some cases even divide such polynomials, but division is not required for this, for the talk. So how do we add and subtract? So you just add it coefficient wise. So suppose you have two infinite degree polynomials. Let's call this fn. So let's call this fn, and we have something gn, so which is a different infinite degree polynomial where the coefficients are, say, bk. This is gn. Then fn plus gn is just this polynomial where the coefficients are now ak minus bk, q to the k, and k goes from 0 to infinity. So this is what I mean by addition of two such infinite degree polynomials. And similarly for, sorry, this should be a plus. Similarly for difference. So if I have a difference here, then I'll just have the difference of the coefficients. Product is a bit more complicated. So if you think carefully, then the product will be something like ck qk, where k is going from 0 to infinity, and here ck is actually a sum of this sort. So k minus l, and l is going from 0 to k. Okay. So this is what I mean by product, and this is called the Cauchy product. It's not very difficult to prove this. So if you just sit down and try to expand it coefficient wise, you'll get what is written here. So division is a bit more, it's not complicated, but it needs some more conditions, like you need that a0 has to be non-zero and so on. All right. So this is how we are going to work with. So we are in the domain of formal power series. So in the formal approach, we can just expand things like the infinite geometric series. So in the formal approach, if I have something like 1 over 1 minus q, I can just write it as 1 plus q square plus q cube and so on. I don't need to care about what this q is. Similarly, if I have 1 over q to the m, then I can just write it as 1 plus q to the m plus q to the 2m plus q to the 3m and so on. Okay, so this is how the formal approach is going to work, and we can just multiply these things together then. So what this means is that if I just say that 1 over 1 minus q times 1 over 1 minus q to the m is just now multiplication of these two series. Okay, and I have already shown you how the multiplication works before, so at least the formula you know. But the important thing to note is that you can do it only finitely many times. Okay, so if you have sort of like finitely many products, then you can just multiply them and say something about what that finitely many products will look like. So if you go back to the first and second Ramanujan identity, you will see that on the left hand side in the denominator you have a finite product. So it makes sense to just write it in a formal approach. Okay. All right. Yeah, so the point that I want to stress is that in the formal approach, to understand infinite identities, we regard both sides to be just formal power series. Okay, without regard to whether the series converges or not. And this is what we are going to assume from now on. I mean, it's not very difficult to show convergence of the formulas that I'm going to present, but that is not the point of the talk. So I'm just going to assume that everything is like in the formal approach. All right. Yeah, so how do you say that two identities are same in the formal approach? Okay, that is also important to know. So suppose you have something like Fn is equal to Gn, where F and G are what was defined earlier. So if I take F and G to be these two polynomials, then if I say that Fn and Gn are equal to each other, then what I mean is that they are coefficient wise equal. That means AK is equal to BK for all k greater than equal to 0. All right, so this is what I mean by two formal power series being equal. But the thing to note, which I have already mentioned earlier, is that the computation should be finite to calculate any coefficient. If you are going to have some infinite computation to calculate even the coefficients, then you cannot say that these two are equal in the formal sense. That I am going to focus on this talk. So two things, coefficient-wise they are equal, and to calculate the coefficients, one needs to do a finite amount of computation, algebraic computation like addition, subtraction, multiplication, and so on. Okay, so there is another infinite object that we are going to look at, and that is a continued fraction. And what does a continued fraction look like? Probably if you have done a first course in number theory, then you already know what is a continued fraction. So a continued fraction is a fraction which is just continuing, right? So I mean the name is self-evident. So you have something like this. So let's say a0 plus some a1 divided by a2, but this fraction will continue now. So again you have some plus, say a3 divided by a4, and then it is just going to continue. So a5 divided by a6, and then it might end at some point, like here it is ending at a6, but it is not necessary that it has to end. It can be an infinite continued fraction as well. So something like a7, and then it is going on. So just as an example, let's do like a very simple example. So suppose I have this continued fraction. So 1 plus 1 plus say 1 over 2. Then how do I calculate this? It's just normally how you would calculate a fraction. So you start from the bottom. 1 plus 1 over 2 is just 3 by 2. And this is going to be equal to 1 plus 2 by 3. Again, you do what is there in the bottom. So this will be 1 over 5 by 3. And then ultimately, we're going to add 1 plus 5 by 3, which is equal to 8 by 5. So this is the value of this continued fraction. Okay. Yeah, so what I need is an infinite, very specific infinite continued fraction. And this is called the Rogers-Ramanujan continued fraction. But before going to that, let me just introduce something else. So the continued fraction that we are going to consider is just where all of these AIs that I had are 1. So that means it is just 1 plus 1 over 1 plus 1 over and so on. Okay, so it's just this continued fraction and so on. It's just going on. So to analyze such a continued fraction, what we do is we iterate, we truncate it at various places, and then we see what these truncations they give you. Okay. So another way to write a continued fraction is just using something called convergence. So I mean, I'll just show you what the notation. Maybe it's better to do it here. So to write this continued fraction, the notation that I am going to people use is that we just write it as A0, A1, A2, A3, and so on. Okay. So this notation means that you are in this continued fraction. And if there is nothing, so if there is no A0, then you just start with a 0. Okay. And sometimes people also like give a semicolon, so to mean that this A0 is the first term, and then whatever is here is the continued fraction. So by this notation, this is just 1, 1, 1, 1, 1, 1, and so on. Okay. So how do one analyze continued fractions? We analyze it by truncating this continued fraction at different places, and these truncations are called then convergence. So if this is the continued fraction, then the convergence, let's call this P1, P2, and so on. So the first convergence will be just this continued fraction where we are truncating in the first place. The second one would be something like 1, 1, where we are truncating in the second place, and then so on. So P3 is just 1, 1, 1. So this is just equal to 1. The next one is equal to 1 plus 1, which is just 2. And then the third one is equal to 1 plus 1 plus 1. Sorry, which is just equal to 2 again, and so on. Okay. So this is how we are going to analyze the continued fractions. And if you do this, so sorry, I think I made a mistake here. Yeah. So this has to be 1 over 1 plus 1, and this has to go one more step, which is 1 over 1 plus 1. And this is not equal to 2. This is equal to, I think, 3 by 2 now. Okay. So these are the convergence. So if one calculates the convergence of this continued fraction, which I'm not going to do, but I mean, yeah, it's not very difficult to see that this will be the convergence. The convergence of this continued fraction are 1, which I can write 1 over 1. Next one is 2, which I can write 2 over 2, and then 3 over 2, 5 over 3, 8 over 5, and so on. Actually, I have already done this. So you see that these convergence, they appear here. This is the last one, then the one here, then the one here, and so on. Okay. So these are the convergence that they appear. All right. So the important thing is that the nth convergent Pn, it satisfies a very simple identity, which is that Pn is equal to 1 plus 1 over Pn minus 1. So this is just coming from the continued fraction, because everything is 1. So you are the nth convergent will be satisfying this very simple identity with respect to the n minus 1th convergent. Okay. Now again, note that the denominator, so let's call this some star. Note that the denominator of the nth convergent is the numerator of the previous one. So just look at the series that I have written down. So here the denominator of this convergent, which is 5, is the numerator of this convergent. Again, the denominator of this convergent, which is 3, is now the numerator here, and so on. So this 2 appears as a numerator here. This 1 appears as a numerator here. Okay. So this keeps on continuing because of the continued fraction that we have selected. So we can basically write this convergence. So Pn, we can write this as some fn divided by fn minus 1. Okay, because this because then the pn minus 1 will be something like fn minus 1 divided by fn minus 2. So the numerator of the nth convergent is now the sorry, the denominator of the nth convergent is now the numerator of the n minus 1th convergent. So we can write pn in this form, fn divided by fn minus 1. Okay, now if you put this value in the equation star, so now star implies that fn divided by fn minus 1 is equal to 1 plus fn minus 2 divided by fn minus 1. And if you multiply both sides by fn minus 1, what you're going to get is fn is equal to fn minus 1 plus fn minus 2. Now, what is f0 and f1? If you calculate f0, f1, I mean f0, yeah, you can just calculate from f1. So f1 will be just 1 and f2 will be 2, right? Because these are the first two conversions, 1 and 2, that we see here. So what you get back is actually the Fibonacci sequence. That means the convergence are related by the Fibonacci sequence. So you know that this is the recurrence for the Fibonacci sequence, and these are the initial values of the Fibonacci sequence. So if the initial values agree and the recurrence is same, then whatever you are going to get is the Fibonacci sequence. So this is a very nice continued fraction, because it gives you, in the convergence, you can find out the Fibonacci sequence. And if you take the ratios, successive ratios, then it approaches to the golden mean. Anyway, yeah, so these are the Fibonacci sequence. Then, I mean, the first result that you can try is, so let's call it a theorem, which is a baby theorem, is that the convergence actually converge. And it converges to the golden ratio. Okay, so which is 1.618 and so on. So I mean, the proof is not very difficult. I'm not going to do it. If you are interested, you can take a look at any probably any. I mean, I think the number theory book by David Burton has a proof of this thing. Even otherwise, you can use a computer to calculate some of the convergence. Say up to n equal to 100 would be enough to show you that there is a pattern. I mean, distinct pattern which shows that it is going to some particular value. Anyway, so this is how we are going to study continued fractions. So what I am interested in is something called the Rogers-Ramanujan continued fraction. So Rogers-Ramanujan continued fraction. And I mean, already from the name, you can guess that it has something to do with the Rogers-Ramanujan identities. So before going to the Rogers-Ramanujan continued fraction, let me again mention one more concept that I'm going to use, which is the Q analog of something. Okay, so the Q analog or the Q generalization of something. So the basic idea is that this number this number n is going to be generalized as a polynomial in Q. So n, you can write this as 1 plus 1 plus and so on up to for n terms. Okay, so this is how you can write n. And the generalization of this, the Q analog or the Q generalization of the number n, is now you are going to add one part of Q to each of the successive terms. So the first term you're going to add Q to the 0. I mean, you're going to multiply it by Q to the 0, which is just 1. The next one, you're going to multiply it by Q to the 1, which is Q. The next one, you are going to multiply by Q square, and then so on, up to Q to the n minus 1. So this is the Q analog of n, and this is denoted by the notation nq. So this is the Q analog, and this is equal to, you already know that this is equal to Q to the 1 minus Q to the n divided by 1 minus Q. All right, so I mean, you can generalize everything now using these particular, I mean, you can call it as a definition. So what about n factorial now? The Q analog of n factorial? I mean, sorry, the Q analog of n factorial is now just 1q times 2q and so on up to nq. And similarly, any binomial coefficient, you can just generalize it. So if you have some binomial coefficient nk, q, then this is now just nq factorial divided by k q factorial times n minus k q factorial. So this is now the Q generalization of the binomial coefficient, which is called the Gaussian binomial coefficient, if you are interested in the name. All right, so what we want is a Q generalization of the continued fraction that we had. So the continued fraction, remember, that we had was something like, sorry, 1 plus 1 plus 1 plus and so on. Okay, so this was the continued fraction, and we are going to do the Q generalization of this continued fraction, and we are going to say that the Q generalization is 1 plus Q divided by 1 plus Q square divided by 1 plus Q cube and so on. Okay, so then you have Q4 and so on. So in each successive level, you are going to multiply it by a power of Q, and you are going to start it by Q to the 0, you are going to multiply it here, then Q to the 1, you are going to multiply here, Q square, Q cube, and so on. So this is the Q generalization of the infinite continued fraction that we had before. So what about the convergence? So if you calculate the convergence here for this Q generalization, the convergence are 1 plus Q, then 1 plus Q square. So I'm going to like sort of write down, because I'm not going to calculate, it's very time consuming otherwise. But I mean, if you can believe me, or you can do it on your own later on. So this will be the convergence of these continued fractions, right? So now we'd like to use a previous convergence step to calculate the next step, like we did before. No, so if you remember, we had this very nice nifty identity that Pn was related to Pn minus 1 by this equation star. So we want to do something similar here, or I mean, even not if something similar, we want to use one convergent to get to the next convergent or something like that. Okay, so what do I mean by that? So for example, if I want to calculate this convergent, so let's say 1 plus Q square plus 1 plus Q cube by 1, then I want to use the previous convergent, which is just 1 plus Q divided by 1 plus Q square by 1. So I want to somehow use this convergent to calculate this. But if you look at the powers of Q are not right? So because here you have Q3, but here there is no Q3. So the powers are not really right to do this. So we are going to adjust this by adding another parameter to the continued fraction. I mean, already we have added a parameter Q to this continued fraction, but we are going to do a further generalization of this Q continued fraction, and then we are going to add one more parameter. So what we are going to do is we are going to call a new continued fraction CZQ, and this CZQ is now 1 plus ZQ. Instead of Q, it's ZQ plus ZQ square divided by 1 plus ZQ cube, and so on. So everywhere I'm adding a Z. Okay, so what this gives us is CZQ. So you take 1 plus Z, and then you take ZQ. But if you look at what is here, this is the same thing as CZQ, but instead of Z, you are multiplying everything by ZQ. So if instead of multiplying here by Z, if you multiply it by ZQ, then you would have gotten this term. So what you have below in the bottom is just CZQQ. Okay, and this is a very nice relation that you have now found for the two continued fractions. So let's call this, I mean, 3. Let's call this 3 because 1, 2 were the Rogers-Ramanujan identities. All right, so this is the Rogers-Ramanujan continued fraction that we are going to use to sort of say something about the Rogers-Ramanujan identities. If you do some of the first few convergence, then you can see a clear pattern. So I'm not going to calculate it properly, but I'm just going to write it down. You can ask a computer to do it for you. I mean, or you can do it by hand. It's not very difficult. So the first one is just the term 1. And the second one, which I'm calling C1ZQ, is now 1 plus ZQ divided by 1, which is just 1 plus ZQ. So if you do this, then the next one, if you truncate it in the second level, is going to be 1 plus ZQ square divided by 1 plus ZQ square. And I'm going to write 2 more. So C3ZQ, which is now 1 plus ZQ square plus ZQ cube plus Z square, Q to the 4 divided by 1 plus ZQ square plus ZQ cube. And then one more I'm going to write. All right, so this is important, so bear with me because I know it is tedious to just see and write from the notes, but all right, so sorry, this is a 2. So 1 plus zq square plus zq cube plus zq to the 4 plus z square q6. Now if you look, you can see some sort of pattern which is emerging. Okay, so for one, if you look in the numerator here, there is nothing in the denominator. So if you look in the numerator, you see that the highest power is just q to the 1. Similarly for 2, the highest power is q square. For 3, it is q4, and for 4, it is q6. So and in the bottom, it's again having a similar sort of pattern. So you start with 2, then 3, then 6, and so on. Okay. So what you can do from here, I'm going to do one more step. So let us I mean, yeah, if you look here, so you see that. So what I want to say is that, yeah. So for example, if you look here, this numerator, if you compare it with the previous numerator, you'll see that it's 1 power more. Similarly here, okay. If you look at the previous numerator, again here, okay. So what I'm going to write is the following. So let the numerator of Cn zq be something called Hn zq. Then we can write Cn zq is equal to Hn zq, but instead of zq, we'll have zqq in the numerator, because you are increasing it by you are multiplying it by zq here. If you see, if you look here, you had just zq, but here if you multiply it by zq, then you get zqq. Again, similarly here, zq cube is just zq times q square, and zq square is just zq times q1. Okay, and so on. Okay, so we have this here, and I mean, you can write this as 1 plus zq times Hn minus 2. If you use the original definition of the continued fraction, zq square divided by Hn minus 1 zqq. Okay, so this is true for at least n equal to, I mean, it is true for at least n equal to 2, 3, 4. Okay, we don't know so far. So this actually suggests that you can reasonably guess that now if you have just, instead of the convergence C and ZQ, if you just take the whole continued fraction CZQ, then you can write it as some HZQ instead of HN. You can write it as some HZQ divided by HZQQ. So this is a reasonable substitution assumption that you can make. And if you remember the nice identity 3, if you use this identity now that we had here, then you get the following. So what you get is HZQ divided by HZQQ equal to 1 plus 1 plus ZQ, then HZ square Q divided by HZQQ. Again, we can just multiply out HZQQ. Then what we have is HZQ is equal to HZQQ plus ZQ times HZ square QQ. Okay. So we want to solve this recurrence. Let's call this 4. So we want to solve this recurrence to say something about the original Rogers-Ramanujan continued fraction. So we are going to use another trick, okay, here to solve this recurrence. So we are going to assume that the solution has a power series expansion. Okay, assume that the solution has a power series expansion. And let's call this HZQ to be equal to k equal to 0 to infinity AKZK. Okay, I mean it will be a power series in Z because we have this this new parameter Z here. Okay, so let's assume that we have something like this here. So what we get from here, if you look at 4 back, so if you just put this value, let's call this A, then if you put A in 4, what you have is the following. So AK ZK, K from 0 to infinity. Now instead of z, you have here zq. So what you will get is ak qk zk, k going from 0 to infinity. Then instead of z, you have z square q, and you are going to multiply it by zq from outside. So zq times k equal to 0 to infinity, ak zk times q 2k. So if you put this inside, then you can just write it as z 2k plus 1 and k plus 1. Okay. So this is what you have got. Now you can just compare the coefficients. Remember, when we said the two power series are equal, it means that the coefficients are equal. So these two sides, if they're equal, then it means that the coefficient of z to the power k will be equal to each other. So if you just compare the coefficients, then you will get from this side, comparing the coefficient of the kth power, you get ak. From the other side, you get ak times qk, because there is a qk here. And from this side, you get ak minus 1 times q 2k minus 1. Because the coefficient of z to the power k plus 1 is now ak, not the coefficient of zk. So you have to go one step back. So the coefficient will be ak minus 1 times q to the power 2k minus 1. And from here, you get a nice formula for ak, which is q to the 2k minus 1 divided by 1 minus q to the k times ak minus 1. So very nice. We have got what the coefficients are related to each other by. We have a formula for them. And what this allows is that it allows us to reiterate to the next step. So here ak is related to ak minus 1. So if you go to the next step, you can just relate ak to ak minus 2. If you just go to the next step, which will be something like 2k minus 1, then q to the power 2 k minus 1 divided by 1 minus qk times 1 minus qk minus 1 a k minus 2 now. Okay, so we are going to use this formula repeatedly, and if you do this after after k iterations, what you are going to get back is a to the power 2k minus 1 plus this thing is now 2k minus 3 and so on up to 1 divided by 1 minus qk, 1 minus qk minus 1 up to 1 minus q times a0. Now this is just the sum of the first k odd numbers, which is equal to q to the k square, right? And in the bottom you have a product, so 1 minus q to the n, where n is going from 0 to k times a0. Now you have already seen this term before. If you remember, if you go back to the first thing that I wrote down, the first thing that I wrote down was the first Rogers-Ramanujan identity, and what you got for the coefficient of this power series is exactly the terms in the left-hand side of the first Rogers-Ramanujan identity. So gradually we're approaching how to sort of like assume, sort of like conjecture the Rogers-Ramanujan identity. All right. So we have got the value of ak in terms of a0. Now a0 is not difficult to calculate. If you just compare the coefficient of a0, then you'll see that a0 is just 1. Okay, so what we have got, sorry. Yeah, what we have got is the following. So take a0 equal to 1, then we get so remember, HZQ was this power series, AK, ZK, 0, and we have found AK. AK is nothing but QK square divided by product of 1 minus Q to the n, and goes from 1 to K times ZK. So this is what we have got. Okay. I'm going to use a very nice notation here, which I'm going to introduce now. The notation is the Q Pockhammer symbol. So it's called QQK ZK. So the notation that I'm using is the following. So AQK is now this product 1 minus A, 1 minus AQ, 1 minus AQ square up to 1 minus AQ to the power K minus 1. So this is the notation that I'm using. instead of writing products everywhere, I'm going to use this Q-Poghammer notation. Okay, so this is called Q-Poghammer notation. And you can also write AQ infinity. It's just now the limit of k goes to infinity for AQK. So it makes sense to also take the infinite product here. All right. So we have found HZQ, which is something like this. So remember, HZQ was just the numerator of this product, numerator of the continued fraction, Rogers Ramanujan continued fraction, HZQ. But what we are interested in, if you go way back, we were interested in originally discontinued fraction. Okay, so discontinued fraction is just C1Q, because if you put z equal to 1, you get back discontinued fraction. So what we have actually found is the following. So we have found that C1Q is now equal to H1Q divided by HQQ, because in the numerator we had ZQQ. And if you put what we have got earlier, we get 0 to infinity QK square divided by QQK, and then 0 to infinity. So here ZQ, Z to the power K, in the numerator Z is equal to 1, so the Z to the power K disappears. But in the denominator, Z is equal to Q. So if you just put a Q here instead of Z, then you are going to get Q to the power K square plus K. So Q to the power K square plus K. QQ K. Again, if you go back to the very top, then what we have is actually the left-hand side of the second Rogers-Ramanujan identity. So in the second Rogers-Ramanujan identity, instead of n square, we had n square plus n. So what we get now is the other side, other Rogers-Ramanujan identity. So the Rogers-Ramanujan identity, the Rogers-Ramanujan continued fraction is actually a ratio of the left-hand side of the first Rogers-Ramanujan identity and the left-hand side of the second Rogers-Ramanujan identity. But what about the product side? So can you also get the product side of the Rogers-Ramanujan identity from some other object? So how do you guess this? Okay. So let us consider H1Q. Okay, so let's consider H1Q. So if you expand H1Q, which is this thing, if you expand H1Q, then the first term is 1 plus Q over 1 minus Q. The second term is Q square divided by 1 minus Q times 1 minus Q square, and so on. Okay. Now, I already told you that you can write this 1 minus Q and 1 minus Q square, etc. You can write it as an infinite geometric series. So what you have basically is something like 1 plus Q square, and so on, plus Q to the power 4, 1 plus Q square, and so on, times 1 plus Q square, Q to the power 4, and so on, plus and so on. Okay. Now, if you see here, the first term will be 1, because this 1 is not multiplied with anything. The second term will be Q. Okay, so if you're arranging by higher powers of Q, so the second term will be Q, which will come from this thing, Q times 1. And then in all the other terms in the sum, there is no possibility of getting a Q, because 1 is always multiplied by some higher power of Q. Okay, it is never multiplied with a Q. So you'll have 1 plus Q plus higher powers of Q. So right now I don't want what the higher powers of Q are. Okay, so plus some higher powers of Q, right? So we will actually eliminate the smallest power of Q from this right hand side. So the smallest power of Q is just Q. Okay, here. So we are going to eliminate this from the how do I say, from the right hand side. So how do you do this? We're just going to multiply everything by 1 minus Q. So H1Q, if you do this, then if you go here, what it means is just 1 plus Q to the power 4 by 1 minus Q square, and so on. Okay. So if you are going to multiply this 1 minus Q, this will be 1 minus Q. This thing will become 1 minus Q, and then this denominator will disappear. So what you are going to be left with is just Q. So 1 minus Q plus Q, you are going to get back the 1. In the next term, this thing in the denominator will go out. So you are going to be left with just 1 minus q square and so on. So if you expand this, you are going to now start with 1 plus q to the power 4 plus higher powers of q. Okay. So you are going to get higher powers of q here. So again, we are going to take out the lowest power of q. So to do that, we just multiply it by 1 minus q to the power 4 this time. So what we get is 1 minus q times 1 minus q to the power 4 times this is h1q. h1q is just now 1 plus q to the power 6 plus higher powers of q. So if you do the same thing like we did before, the lowest power of q that will appear is q to the 6. So I'm not considering q to the 0. Again, using the same trick, you just eliminate the power q6. So to do that, you are going to multiply it now by 1 minus q to the 6. And you can keep on doing this. Okay. So if you keep on doing this, what you are going to eventually get is that you started with h1q, and then you multiplied by successive differences of the highest power with 1. So you started with 1 minus q, then you went to 1 minus q to the 4, then you are going to go to 1 minus q to the 6, and then the next higher power will be q to the 9 if you do it. So you are going to q to the 9 and so on. So you keep on multiplying with the higher powers of q. So eventually it will happen that there is no power of q that you are going to multiply, because if you multiply everything on this side, then you are going to be just left with 1 here. Okay. So this is, I mean, for analysts who are in the audience, probably this is very horrible, but since we are in the formal approach, we don't care about what convergence or everything of this of the series and products. So we just say that coefficient wise they're okay, equal. So eventually we're going to be left with just 1, because we have eliminated all the powers of q by multiplying successively with 1 minus q to the power 4, etc. So if you have taken out all the powers of q, what is remaining is just 1, because the first term is always 1. Okay. So this is what we have got. Now, if you just look at the product, so what you can write down is the following now. h1q is now just 1 divided by 1 minus q to the 4, 1 minus q to the 6, 1 minus q to the 9, and so on. Okay. And this is just 1 minus q to the 5m plus 1 times 1 minus q to the 5m plus 4, where m is going from 0 to infinity. So these two things are the same. So if you again go back to the very top where we have the Rogers-Ramanujan identities, you'll see that what we have got is exactly the left-hand side of the first Rogers-Ramanujan identity. And if you do a similar approach with h, instead of h1q, if you just do the same approach with hqqq, then you will get the other side of the right hand side of the second Rogers-Ramanujan identity. So hqqq will be now the right hand side of the second Rogers-Ramanujan identity. So so remember, we started with this. So c1q, h1q divided by hqqq was this thing, and we have proven that h1q, which is the numerator, which is this thing, is also sort of like equal to this particular object. So that means we have kind of guessed what the first Rogers-Ramanujan identity is, because you just compare this formula, let's call this a B. If you compare the formula B with what we have here, then you will be able to write down the first Rogers-Ramanujan identity. And if you compare it with the second part, HQQ, then you are going to be able to write down the second Rogers-Ramanujan identity. So remember, this is not a proof, but we have just sort of like guessed from a very elementary math techniques in algebra how to conjecture the Rogers-Ramanujan identity. So this approach of like taking out the successive powers, here I have just worked with H1Q and HQQ, but you can do this trick for many different things. So this is a trick due to Euler actually. And instead of starting with H1Q, if you start with zeta s, which is this series, so 1 plus 1 over 2 to the s plus 1 over 3 to the s. So if you start with zeta s, then you are going to get back a very famous sum product formula of Euler. So there is a famous formula of Euler, sum product of yeah. So I mean, for those who know this formula, so I'm not going to write it down, but if you do the same exercise, you are going to get back the Euler's formula. All right. So let's just summarize what we had until now. So this is sort of like the end of the first part, where we can, I mean, I have shown that how Ramanujan or probably Rogers might have found the Rogers-Ramanujan identities. I mean, I doubt if Rogers did this approach, but might be Ramanujan probably was familiar with these techniques, because he was an expert in manipulating sort of like infinite series and products. So the summary is that first we give a Q generalization of the continued fraction for the golden mean or the golden ratio, and this Q generalization was the Rogers-Ramanujan continued fraction. Next, an analysis of this Rogers-Ramanujan continued fraction led to the sum side. So led to the sum side with these ratios of H1Q and HQQ. Then we used another trick. Then we used a trick of Euler of removing the successive successive smallest powers of Q to get the product side. So this is sort of like the summary of what we have done so far. So this is one approach of how one might sort of try to conjecture Rogers-Ramanujan identity as well as other type of identities. Okay. Now I see that I am already, I thought I'll do it in 45 minutes, but I am already over time. So let me just go to the next portion, where I wanted to do a proof of the Rogers-Ramanujan identity, but if I do the proof, then it will take me about 15 minutes to do it. So instead of doing the proof, which is not difficult, but if one is not familiar with Q-series manipulation, then one needs to go through it line by line very carefully. So which I wanted to do, but anyway, so I'm not going to do the proof, but I'll give you the reference where you can find. So there are two nice places where you can find two different proofs, two very nice proofs. So one is already the book by Andrew V. Sills in chapter 2, I think, probably. Yeah, I'm not sure. So page number 74, probably, in the book by Andrew V. Sills. And the other is chapter 19 of the very nice book by Hardy and Wright called An Introduction to the Theory of Numbers. There is a chapter on integer partitions where the Rogers-Ramanujan identities appear, and there is a proof of the Rogers-Ramanujan identity. So you can take a look at them. What I'm going to do now is actually give a combinatorial interpretation to the Rogers-Ramanujan identity. And this interpretation is due to Isai Schur. And this allows me to actually introduce a class of objects which I like very much, and these are integer partitions. So let's go to the second part of the talk that I wanted to discuss. I mean, it's really the third part because I wanted to do the proof, but I'll just skip it now. So let me write down the, yeah, before that, let me just introduce what is a partition, okay? So a partition, lambda of an integer n, so of an integer n, is a finite sequence, say lambda 1, lambda 2, up to lambda L, such that lambda 1 is greater than or equal to lambda 2, which is greater than or equal to lambda 3, and so on, up to lambda L, and lambda 1 plus lambda 2 up to lambda L is equal to n. So this is what I mean by partition. Basically, it's just breaking up a number into smaller bits, okay? And all of these has to be positive. For example, there are 5 partitions of 4. So you can write 4 as just 4. You can break it into 3 plus 1. You can break it into 2 plus 2. And you can break it into 2 plus 1 plus 1. And the fifth thing that you can do is you can just break everything into ones. So these are the partitions of 4. We call each of them a partition of 4. And each of these terms that appear in this partition, so for example 4, then in the next one 3 1, then in the next 2 2, then in the next one 2 1 1, and so on, these are called parts of a partition, okay? the fact that there are 5 partitions of 4, we write it as P of 4 is equal to 5. So Pn is the number of partitions of n. Now, what about a formula for Pn? So here it was easy to see that there are 5 partitions of 4. What about 200? So if you have n equal to 200, it's not very easy to write down all the partitions of 200. So in that case, a formula would be very nice, but unfortunately, there is no easy sort of formula for the number of partitions. So what exists are asymptotic formulas, and there is an algebraic formula now, but it's not very easy to state that algebraic formula, which is due to Ken Ono and some of his collaborators. But there is a nice formula by Hardy and Ramanujan, which is an asymptotic formula for Pn, which gives approximately what Pn is for large n. And that formula was modified by another mathematician called Rademacher, who gave a better estimate for Pn. But we are not going to go into that. What we are interested in are generating functions for partition. Okay, so what is the generating function for partition? So basically, what is Pn Qn n equal to 0 to n? So is there a nice formula for this? And it turns out that there is a nice formula, and this formula is due to Euler. So you can get this formula if you do the following trick. So let's look at 1 by 1 over q times 1 by 1 over q square. So again, we are going to use the formal approach. So this is nothing but 1 plus q square, and then the other one is just 1 plus q to the power 4, and so on. So if you multiply these factors out, then what we are going to get is just 1 plus q to the 1 plus the next thing is you can get q to the 1. So you can get q square in 2 ways now. So the first way is you can get q square times 1 here, and the next way is you can take the q square from here and take the q here. So what you are going to get is something like q square plus q 1 plus 1, which is the same thing. So you are going to get 2 of this. And then similarly, the 3 you can get from here. So you can multiply this q with the q square here and get a q3, or you can let's just write down. So q to the power 2 plus 1, which is what I had, and then you can just get the 3. So which is just q to the power 1 plus 1 plus 1, and so on. Okay. Sorry, I made a mistake. So I don't want the second one. I just want the first one, which is 2 plus 1. What about q to the power 4? You can get q to the power 4 from q square, which is q2 plus 2, or you can get q to the power 4 just here, which is nothing but q1 plus 1 plus 1 plus 1. Okay, and I think there is one more q square that you can get. So which will be q square plus 1 plus 1, and so on. So what we're getting after multiplying these two infinite series is all the partitions of n which are made of parts 1 and 2 only. So if you look at the exponents here, if you look these two exponent, these are the partitions of 2 which are made of the parts 2 and 1. Similarly, this is the partition of 3 which is made with the parts 2 and 1. And these are the 3 partitions of 4 which are made from the parts 2 and 1. So what this is giving, this thing is giving, the left hand side are just the partitions in parts 2 and 1. So if you keep on doing this, eventually if you multiply all of the things here, so if you do 1 by 1 over q times 1 by 1 over q square times 1 by 1 over q3, then you are going to get all the partitions which are given by the parts 1, 2, and 3. So if you keep on doing this, then you are going to eventually get all the partitions of given by any of the parts. So basically what you have proven is a result of Euler, which is that the generating function of the partition is nothing but this infinite product, 1 over q square, 1 minus q, and so on. So this is the infinite product. And if you remember the notation, this is just 1 over q infinity. All right. So this is a very famous result, at least the starting point of the result by Euler. There are other results by Euler which are not very difficult to prove. For example, the number of partitions into odd parts is equal to the number of partitions into distinct parts. Okay. So what it means, let's look at an example. So let's look at the initial example that we had. So there were 5 partitions of 4. Sorry, this is 3 plus 1. Then you had 2 plus 2, then 2 plus 1 plus 1, and then 1 plus 1 plus 1 plus 1. So what is the so what is the number of partitions into odd parts? So that means the partitions where only odd parts appear. So one is this, where 3 and 1 both are odd. This cannot be because 2 is an even number. Similarly, the 4th one cannot be because 2 is an even number. But this is a partition which is given in terms of only odd parts because 1 is odd. So that means this part, this side is 2 for n equal to 4. And what about the partitions into distinct parts? So if you look at 4, this is a partition into distinct parts because there exists only one part and which is distinct. No other part is the same. So you get 1. If you look at the second partition, 3 plus 1, again, this is a partition into distinct parts because 3 and 1, they are different. But this is not a partition into distinct part because 2 is the same. Again, this is not a partition into distinct parts because 2 ones appear. And similarly, this is not a distinct partition because 1 appears 4 times. So again, this side is also 2. That means you have verified Euler's result for n equal to 4. In general, this is true for all n. And the proof is not difficult, but since we don't have much time, so I'm going to skip it. There are actually very nice proofs. So for example, there is a proof by, there is a very nice combinatorial proof by Sylvester, which is quite instructive. So if you want to look at it, so you can take a look at. So this is J.J. Sylvester, around I think 1890s, somewhere around. So there's a nice proof by Sylvester. Anyway, so what I want to do is a different theorem. So which is the following. So I'm going to state the result, and then we'll see how this connects with the Rogers-Ramanujan identities. So the result that I want to do is the number of partitions of n with at most L parts equals the number of partitions of n with the largest part equal to L. At most L. So let us look at two sides separately. Okay, so what is let's try to figure out what is the generating function for the left hand side first. So by the left hand side I mean this part, so the partitions of n with at most L parts. So if there is just one part, then the generating function is just 1 over 1 by q. 1 over 1 minus q. And if there are 2 parts, then you had that this was 1 over q times 1 over q square. So you can keep on doing this, and you can stop at when the power of q is L. So that means the generating function for the left hand side is something like this. So 1 over 1 minus q square up to 1 minus q to the L. So this is the generating function for the So let the number of partitions of n into at most L parts be say PL. Okay, so by at most L parts, I mean that the partition can have 1 part, 2 part, 3 part, up to L parts. So the number of say partitions of n with exactly L parts is now equal to PLN minus PL minus 1n. So you are just going to take out all the partitions where the number of parts is at most L minus 1 from the number of partitions where the number of parts is at most L. So you are just left with all the partitions where there are exactly L parts. So this is what we have. So what is the generating function now? So for this, the generating function for this is now just the difference. So 1 minus 1 over 1 minus q square up to 1 minus q to the L minus 1 minus q square up to 1 minus q to the L minus 1. So if you just do some simple algebra where you just multiply this thing with 1 minus q to the L in the numerator and denominator, what you are going to get is q to the L divided by this 1 minus q square up to 1 minus q to the L. Okay, so this is fine. So let's call this A. Okay, so let's call the number of partitions with exactly L parts to be equal to P and L. Okay, then what we have is the generating function for P and L, q to the n, is nothing but A. Okay, so this is the generating function for P and L. Now if you sum over all the L's, that means you count the number of partitions of n with at most 1 part, with at most 2 parts, with at most 3 parts, and so on up to n, then what you're getting back is basically the number of partitions, right? Because all the partitions will be just, it will belong to just one of these particular classes. It will have either 1 part, it will have 2 parts, or it will have at most n parts, where all of them are 1 plus 1 plus 1 and so on. So what you get from here is that basically the generating function for all partitions is nothing but the sum over all L for sorry, yeah, it's fine. So L equal to infinity. So let's call this AL. It will make more sense over AL. So AL is this thing now. So what you have proved, or at least what we have sort of like understood from this whole thing, is the following. So remember Euler's result. Euler's result was that Pn, Qn, the generating function, is a nice product, which is QQ infinity, which is just 1 over 1 minus q to the L product, L equal to 0 to infinity. And here, this is equal to sum over L equal to 0 to infinity, q to the L divided by 1 minus q square up to 1 minus q to the L. So again, you see that this is sort of like a Rogers-Ramanujan type identity, where you have an infinite product on one side and you have a infinite sum on the other side. It's not exactly the Rogers-Ramanujan identity, but you get sort of like a proto-Rogers-Ramanujan identity. Okay, so let's go back to the Rogers-Ramanujan identity. You see, we see that there is some sort of connection with integer partitions. So what is that connection? I'm going to now state the combinatorial interpretations of the Rogers-Ramanujan identity. So combinatorial interpretation of the Rogers-Ramanujan identity. And this is first due to Isai Schur, who was a famous algebraist, number theorist from Germany. And I think this was around 1930s, if I'm not wrong. Yeah, I don't remember exactly. So the first Rogers-Ramanujan identity is nothing but the following theorem for integer partitions. So what it says is that the number of partitions of n into parts which differ by, so which differ from each other by at least 2 equals the number of partitions of n into parts which are congruent to plus minus 1 mod 5. And then similarly, the second one, second Rogers-Ramanujan identity is that the number of partitions of n into parts greater than 1, which differ from each other by at least 2 is equal to the number of partitions of n into parts which are congruent to plus minus 2 mod 5. So the next task in the next 10 minutes or so that I have is to show at least one equivalent. So let me just take the first one, and we are going to see that what the first interpretation is saying is exactly the first Ramanujan identity. Okay. So just as an aside, I mean, if you look here, the interpretation is based on parts which differ by at least 2. So if you go back to Euler's result, where so this result where it says that the number of partitions into odd parts is equal to number of partitions into distinct parts. So by distinct parts, what you mean is that each part is differing by at least 1, because if there is a difference of at least 1, then that means the parts are distinct. So Euler's result is actually in the same class of results that this is that this combinatorial interpretation is saying, but it's sort of slightly different. So instead of just taking by at least 2, you can also ask what happens if you take by at least 3. Again, there is a result for that, which I'm not going to discuss. Then instead of mod 5, you have to work with partitions into parts which are in the equivalence classes mod 6. Okay, so let's look at the first interpretation. So let say R1n is equal to the number of partitions of n into parts which mutually differ by at least 2. Differ by at least 2. So, and then let's say R2n is now the number of partitions of n into parts which are congruent to plus minus 1 mod 5. So the next the generating function for R2n is not very difficult to see. So you have already done actually. So what is the generating function for R2n qn? This is just you take all the parts, you take all the powers of q which are congruent to 1 mod 5, which is something like 5m plus 1, and then you take all the powers of q which are congruent to minus 1 mod 5, which is just 1 minus q to the power 5m plus 4. So by we have already seen 2 times. So by the trick of Euler, if you just do the infinite product here, then you are going to get the generating function. Okay, so you are going to get back the generating function for this. And if you remember, now you have seen it multiple times already. So if you remember, this is exactly the right-hand side of the first Ramanujan identity, where you had 1 minus q to the 5m plus 1 times 1 minus q to the 5m plus 4. So you have already got back at least one side of the Ramanujan identity. So if you can show that the generating function for R1qn is nothing but the left-hand side of the Ramanujan identity, that means it is a sum over q to the n square divided by that finite product, then by a proof of the Ramanujan identity, which we did not see, but there exists a proof. So you can say that since these two generating functions are equal, so that means the coefficients of that generating function are also equal, which means that R1n is equal to R2n, and which is just what the first sentence is saying, first statement is saying. Okay, so this is a combinatorial interpretation in terms of integer partitions for the Ramanujan identity. So let's see what is R1n. So for to see what is this generating function, we are going to work, instead of working with partitions, we are going to work with tuples of numbers. So if you have a partition, say lambda is a partition, lambda 1, lambda 2 up to lambda m, where m is less than equal to L, then you can make it into a L tuple. So you can convert this partition into a L tuple. What you do is just you take lambda 1, lambda 2 up to lambda m, then you just add a bunch of zeros. So you add a bunch of zeros, and exactly you add L minus m many zeros. So since m is less than equal to L, so you can always do it. You can add a bunch of zeros, and if m is equal to L, you don't add any zeros because you already have a L tuple. So you can convert any partition of a number which with at most L parts into a L tuple. So that means let me just write this down, and then you'll see what I mean. So a partition with at most L parts can be padded with zeros to make a L tuple. So the generating function for such L tuples of, so there is a condition. The condition is that these L tuples are weakly decreasing. So that means lambda 1 is greater than equal to lambda 2, which is greater than equal to, and so on. Okay, so such L tuples of weakly decreasing positive integers is nothing but 1 over QQL, because 1 over QQL was the generating function for partitions with at most L parts, right? So which is what is here, okay, this generating function. So the generating function for the L tuple is exactly the same, because these two things are the same. We have a sort of like a natural map between these two objects. So from here, how does one get what is the generating function for R1? So again, we need to do one more step, and then we'll be done with finding what is R1. Okay, so let's see what that step is. So to this L tuple, we are going to increase the first component. Say lambda 1, we are going to increase it by 2L minus 1. The second component, which is lambda 2, we are going to increase it by 2L minus 3. The third component, lambda 3, we are going to increase it by 2L minus 5, and so on. Then the last second component, we are going to increase it by 3. So and the extreme last component, we are going to increase it by 1. So that means we are gradually increasing it by 2L minus 1, 2L minus 3, and so on, up to 3 and 1. Since the last things were just zeros, so I'm not adding the 0, but I mean, if you want, you can add 0 plus 1, 0 plus 3. Okay, so what we have here is actually, I mean, this is the same thing. So combinatorially, you have made one object into a different class of object by just adding a very fixed quantity. So there is not, so the number will be the same, but the generating function will differ. So what is the generating function? The generating function for such L tuples is now, since you are adding a 2L minus 1, 2L minus 3 up to 3 and 1, so you have to increase it by q to the 2L minus 1 times q to the 2L minus 3 times up to q to the 3, q to the 1. So this is going to be there in each of the L tuples, and whatever was there remaining. So the numerator was, sorry, the denominator was QQL. So what you have here is nothing but q to the L square divided by QQL. So now you see that this is at least the terms which appear in the right hand side of the first row as a Ramanujan identity. It's actually a sum. So how do you get the sum? But this is nothing but a partition generated by R1Ln. So the generating function for R1Ln is just a sum now. So q to the L square divided by QQL. where L is going from 0 to infinity. So why is this nothing but a partition generated by R1? See, first you started with a partition, lambda 1, lambda 2 up to lambda m was a partition, and then you added a bunch of zeros, which is still a partition. So, I mean, it makes no difference because the sum is again giving some finite number. But to that L tuple, you have now added further 2L minus 1, 2L minus 3, and so on. So if you look at the difference, if you look at the successive differences, you see that the successive differences are at least 2. Because even if lambda 1 and lambda 2 were equal, it cannot be that lambda 2 is greater than lambda 1. So the maximum it can be is lambda 2 is equal to lambda 1. Even if they were equal, in this particular L tuple, since you have added 2L minus 1 to one and 2L minus 3 to another, so the difference will become at least 2. Okay, and similarly for these two cases, so for lambda 2 and lambda 3, again the difference will be at least 2 between this whole part and this whole part. So which is exactly what R1n was counting, because this was the number of partitions into parts which mutually differ by at least 2. Okay, so if you just sum over all the possibilities of L, since L is just a fixed number, so L can vary from 0 to up to whatever you want. So if you just count over all the possibilities of L, you are going to get back the generating function for R1n. So now you have also got back the left hand side of the Ramanujan identity. If you remember, this was the left hand side of the Ramanujan identity. So since you already have, I mean, okay, you are assuming that you have a proof of the analytic proof of the Ramanujan identity. So it means that this generating function R1 NQN and R2 NQN, these are equal to each other, and by our formal approach, if two generating functions are equal, then the coefficients are also equal. So that means R1n is equal to R2n, and which means that this combinatorial interpretation is correct. So similarly, you can also do the second combinatorial interpretation, where you don't have now the part which is equal to 1, and because you don't have the part which is equal to 1, then you will get something different in the numerator. So instead of L square, you get L square plus L. Okay, so I'm already actually done. So this is what I wanted to say, and I'm happy to answer the question now.